All right, gang, here we go. This is Chem 1, Unit 7, Part 1. We're going to talk about balancing chemical equations. Today should be pretty fun, not too hard. All right, so first off, when we start, we just need to establish what chemical equations are real quick. So anytime you want to communicate anything, you have to have some sort of standardized method of communication. Okay, and so just like in math, you use everybody across the world uses the same positive minus symbols to represent plus, minus, etc. We have to have some sort of way of communicating chemical ideas. So in order to do that, we're going to use these things called chemical equations in order to represent when a chemical reaction takes place. All right. So this is how they are always written. Okay. We always write reactants and then an arrow and then products. Reactants yield products. Okay. We can also represent what elements or what the states are of the elements that are there. Look, the parentheses got lost. Anyway, so this means that whatever it's next to is a solid. Okay. And then this means whatever it's next to is a liquid. Okay. And I'll bet you can guess what the G is for. That's right, it's for gas. Now the last one is aqueous. All right. AQ stands for aqueous. Okay. And this means something was dissolved in water. Okay, that means, so aqueous, dissolved in water. All right. Okay, now one thing to note is that when we're talking about liquids, primarily when we're talking about liquids, we're only going to care about 3 cases. Okay, everything else we look at, it might look like a liquid, but for the most part, they're aqueous because we're talking about solids that are dissolved in water, and water is just the solution or the solvent. We'll talk a lot more about that later. Okay. But for now, primarily you should avoid using liquid unless it's one of these 3 things. Essentially, if you have water in your solution, it has to be a liquid or a gas. You can't have aqueous water because that doesn't make sense. That means you dissolved water in water, and that just doesn't make sense at all. Okay. Another case for liquid are the other 2 main cases for liquids that we'll worry about is if you happen to be using actual liquid mercury. Okay, which we probably won't use in class, but on paper it could come up, right? It's pretty easy to write Hg, all right? And then the other one is if you are using elemental bromine, okay, which is also a liquid at room temperature. We know that because on our periodic table, they're marked that they're liquids at room temperature, okay? This arrow represents that it's a reaction, so it's products, and then this is known as yield. Okay, so you say such and such yields such and such. Okay, reactants yield products. All right. Another couple symbols to be aware of. An arrow that's pointed upwards means that your reaction is giving off or producing a gas. Okay, and then a downward arrow means your reaction is producing a precipitate. Okay, and precipitates are also labeled as PPT. All right. Okay, we can also write out catalysts written above arrows. Okay, so there's a lot on this slide, and so take a moment just to pause the video and take a look. Make sure you understand what all these things mean, and it'll take you time to understand what's going on. So let's look at a couple of these reactions here. Okay, so this guy here, that's silver nitrate, is reacting with sodium chloride. Now, I happen to know both of these guys are aqueous. Okay, so we'll write in that they're aqueous right here, and technically that we would put these in between these symbols that are here, and it's forming silver chloride. Now notice this bottom arrow, this arrow pointing down, this implies that it's forming a precipitate. Well, precipitates aren't in solution anymore. They're solids that have fallen out of solution, so that would be a solid, and then you have sodium nitrate, which is aqueous as well. All right, it makes sense. Okay, then you have calcium carbonate. Okay, so calcium carbonate reacting with HBr. Now, calcium carbonate's an interesting one. Okay, we're just going to assume that it started as a solid just for fun, so just to put that solid. And then this is hydrobromic acid, and all acids will always be aqueous because you never want a solid acid. That's crazy. All right, and then calcium bromide. Okay, so this would also be aqueous. Okay. We'll talk more about how to predict these things later. Now, this up arrow says that it produces a gas, right? So this CO2, we'll add in this gas symbol right here. And this is water. Water can never be aqueous, so it has to be a liquid. All right, so that's how you would use some of those symbols. Okay. Chemical reactions occur when one substance changes into a new substance. It's pretty easy. And remember, way back in the first unit, we talked about signs of chemical reactions. So maybe make sure you're familiar with those. All right. Balancing chemical equations. Now, anytime you write out a chemical equation, you always have to make sure it's balanced. Now, what does that mean? Well, let's take a step back here, talk about a couple of things. Law of conservation of mass. Well, let's just break this down. Conservation means keep. Okay, like if you want to conserve the rainforest, you want to keep them exactly the way they are. And then mass, that's how much matter there is. So essentially the law of conservation of mass says is that we have to keep the same amount of mass, or keep the same amount of matter. Okay, so essentially what we're saying is that if we start with a certain amount of hydrogen, we have to have that same amount of hydrogen at the end. Okay, and that follows Dalton's atomic theory. Okay, during a chemical reaction, atoms are not destroyed, they are simply rearranged. Essentially, we're breaking and forming those bonds between the elements. Okay, so balancing a chemical equation, this is the foolproof method to help you always get it right, but I'm going to teach you some tricks as we work through these other practice problems. The thing that you need to pay attention to is that we only change the coefficients. This is the key. All right, we only change the coefficients. All right. Remember, the coefficients are the numbers that are in front of the element. We cannot change the subscript, right? So if we have water, that's H2O, we can't change that 2, because if we change that 2, it's no longer water, right? It would be like HO, which would be hydroxide. Totally different thing. Okay, so we can never change these subscripts. We can only change the coefficient. The coefficient would be that number that goes in front. All right, so let's balance these guys. All right, so when I do these, I simply go from left to right. So I start with the hydrogens. Okay, hydrogen and oxygen, and I just go left to right, and I just balance them. I just throw in numbers until it makes sense. So I've got 2 hydrogens here, right? I know there's 2 because there's a 2 right there, so that's 2 hydrogens, and then 2 hydrogens, so this guy's already balanced. 2 on the left side, 2 on the right side. Oxygen, I've got 1 oxygen, okay, and I've got 2 oxygens. So that means I got to balance it, so I'm going to put a 2 out front here. So now I've got 2 oxygens here, and I've got 2 oxygens here. Notice that I did not write a 2 down here, because that would make it so I no longer had water, I had hydrogen peroxide. That breaks it. We don't want that. Okay, so I'm going to put that 2 out front. Okay, but now that changes the number of hydrogens that I have, right? So I can only have 4 hydrogens. All right, here I have 4 hydrogens and 2, so I got to throw that 2 in there as well. So now it's all balanced because I got 4 hydrogens, 2 oxygens, and 2 oxygens. All right, let's try another one. So we got zinc, hydrochloric acid yields zinc chloride and hydrogen. All right, so zinc, so we've got 1 zinc, 1 zinc. Good. All right, now we got hydrogen and 2 hydrogen. Oh, that's no good. So we'll throw a 2 here for that hydrogen. All right, and then we got 2 chlorines now, right, because of that 2. And then we got 2 chlorines here. So now we're all balanced. Easy peasy. All right, let's try this guy here. Iron hydroxide yields iron oxide and water. Water, right? All right, so let's balance. So we got iron. We got 2 irons here, so we need a 2 here for this iron. So now our irons are balanced. Now, so now this is a more exciting one. We have to kind of think about this. So how many oxygens do we have on the left-hand side? Well, we've got 3 of these hydroxides. Remember, this 3 applies to both things because there's a parentheses. So there's 3 oxygens, 3 hydrogens, but we have 2 sets of them. So that means on the left-hand side here, we have 6 oxygens. Okay. On the right-hand side, we have 4 oxygens. 1, 2, 3, 4. All right. So 6 oxygens versus 4 oxygens. Now, what could we do to balance? Well, we could do all sorts of things to balance it, but let's just hold off. Then whenever you're balancing chemical equations, if you run into a case where where you have something that's located in more than one thing on one side, it's almost always easier to leave that towards the end. Okay, and you'll start, as you do more and more of these, you'll start to develop kind of a sixth sense for these things. All right, so let's skip the oxygen for now because there's a couple of different ways we could balance it. All right, let's try the hydrogen. Well, the hydrogen is in the same case. We have 6 hydrogens, right? 3 and then 2 sets of those 3. So that's 6 hydrogens. Over here, we've only got 2, so we'll throw 3 out here in front. So now we've got 6 hydrogens on both sides. All right. Now, what did that do to our oxygens? Well, our oxygens, now we have 6 oxygens on the right-hand side and then 6 oxygens on the left-hand side. So now this is balanced. All right, isn't that nice? All right, now this guy here, C2H6 plus O2 yields CO2 and H2O. We're going to balance this guy. Once again, we're just going to go left to right. All right, carbon. There's 2 carbons here, 1 carbon here, so we'll throw a 2 right there. Hydrogens, we got 6 hydrogens here, 2 hydrogens here, so we'll throw a 3 right there. All right, now let's look at oxygen. This is where these get a little trickier. All right, so we got oxygen here. We've got 2 oxygens. On the right-hand side, though, we've got 4 oxygens and 3, so that's 7 oxygens on the right-hand side. Ooh, now you might be like, oh, no, we can't make 7 because there's 2, and 2 doesn't go into 7. So we're going to break the rules for just half a second. Try not to panic, okay? We're going to assume that we can have half of an oxygen molecule. Can't really happen, but we're just going to assume for a second that we can have half an oxygen molecule. Now, in order to convert all that to the correct notation where we have whole number ratios, all we have to do, now just take a step back. I'm thinking about math for a second. If you had this fraction, 7 halves, and you wanted to convert that to a whole number, all you would have to do is multiply it by 2, right? Because if you took that, multiply it by 2, the 2's cancel, and you're just left with 7. Okay, so we'll multiply all these coefficients by 2. So there's a 1 right there, so 2 times 1 is 2. All right, now we're going to convert the 7 halves, all right, to 2, or multiply that by 2, so the 2's cancel, we're just left with 7, okay? The 2 multiplied by 2 turns into 4, right? 4, and then the 3 turns into a 6, all right? So now we've got a completely balanced chemical equation. We can double check it. We've got 4 carbons on the left side, 4 carbons on the right side, 12 hydrogens on the left side, 12 hydrogens on the right side, 14 oxygens on the left side, and then 4 times 2 is 8, plus 6 times 1 is 14, so 14 and 14. And that's it for balancing chemical equations. Do lots of practice problems. The only way to get good at these is just to do the practice. You can do it. Let me know if you have any questions, and I'll see you on the flip side.